Hi, and welcome back. Now we're going to have a look at Newton's first law of motion. We've looked at how we can describe vectors, use vectors to describe how forces are acting on an object, and how the application of force can change the way that something moves. Newton was one of the first people to describe how, and mathematically, a set of rules to describe motion and what happens to an object due to the presence of a force. And this is what we're going to look at now. There's three laws, and now we're going to look at the first one. So Newton's first law is all about unbalanced forces. And the law simply states that a body, i.e. an object, in motion will remain in motion unless an unbalanced force acts on it. Okay, so this means that a body at rest will remain at rest unless an unbalanced force acts on it. And we talked about this when we were using vectors. This means that for a single object, if it is stationary, we know that all the forces are balanced. Okay, this object would not be moving up or down. It would be sitting simply on the table because it would have the same force pushing it down as opposing that by the table pushing back on it. And this is simply what Newton's first law states, that with no outside forces, a stationary object will not move. Okay, so in order to make it move, we would need to apply a force. Okay, when we apply that force, it will accelerate, it will start to move, it will speed up. So with no outside forces though, a moving object will not stop. So once we've made this object move, and if it is moving with a constant speed, then nothing is going to change the speed of that object until an unbalanced force either speeds it up or slows it down. Something causes it to stop or change its motion. Okay, and we can see this in action when we're driving cars. Okay, if we consider driving a car along the freeway, as we enter the freeway, in order to not collide with other cars, we're going to put our foot on the accelerator. What that's going to do is cause the engine to provide more power, which will increase the thrust on our car. So our driving force will increase. We've still got friction from the road acting on our car, okay, everything like that. So we've got the force of friction, but we know that we're going to accelerate because we are placing extra force in the direction of movement. So our force vector for the thrust is larger than the friction force, so it's going to accelerate. Our forces are unbalanced. But once we're out on the freeway, what we might start to do is put on our cruise control. We've got a long way to drive. We're going to hit the speed that we want to hit. So we'll hit, 100 kilometers per hour. And we click on the cruise control. What that will do is make sure now that the force applied by the engine is equal to, so our driving force is equal to our drag, okay, which is going to be a combination of our friction and air resistance, okay? So now, because those two forces are balanced, we will see constant speed, okay? So as long as there is a net zero force, i.e. our forces are balanced, then the motion of the object doesn't change. So if it is traveling at a constant speed, it stays traveling at a constant speed. If it is stationary, it stays stationary. And that is Newton's first law. An object will not change its motion unless an unbalanced force is applied. So let's think about this in terms of when something starts moving from stationary and whether forces are acting on an object or not. Watch this video and consider this situation. So what we see here is that the truck, initially stationary, flatbed truck, with the car on the back, okay, is initially stationary. The car is not tied down to the truck, it's just sitting on it. So we know it's sitting on it with the force of gravity being equal to its normal force. The truck also has a force of gravity acting on it because it's on the road, and a normal force. And we don't have a thrust or a friction force at the start for either situation. Then what happens is the truck puts the foot on the accelerator and it accelerates forward. Okay, so we know it has a driving force as it accelerates forward, and it has a friction force which is allowing it to gain traction as it moves forward. We know that the driving force exceeds the friction force because it's moving forward. However, the car that is sitting on the truck does not have a driving force that is being applied to it. So what happens is the truck now accelerates away from, the car. Okay, so it's going to accelerate away from the car, but the car is not being moved. There's nothing changing its motion. So then the car now, where it had a balanced force acting on it before, where we had the normal force pushing back, it now has nothing underneath it. So the force due to gravity is here. It doesn't have a driving force pushing it forward or anything pushing it back. So now its forces are unbalanced. It has a force due to gravity and it will fall until it is now resting on the ground. Once it is resting on the ground, we have a situation where our force due to gravity is now being equally opposed by our normal force. So now it stops moving. But this is a classic example of Newton's first law. The truck had a driving force. There was a force being applied to change its motion. But because the car was stationary and there was no force present to change its motion, it stayed in place. And this is why we use seat belts and we tie loads on, because by putting those straps on, those straps will apply a force to hold the load onto the bed of the truck. Okay, and then therefore it would shift a little, but it would stay in contact. We see the same when we're passengers in a car. If a car stops suddenly, we move forward. And this is because our motion, we were in motion with the car. When the car stops, we remain in motion and move forward. Our seatbelts then engage and push us back. If we didn't wear seatbelts, we would continue to move forward and could end up going through the windscreen. So reasons why we need to be wearing our seatbelts all the time. Okay, so let's look at an example that has been shown in your booklet and in some of the other activities that you've done. We can look at the action of a skydiver in terms of Newton's first law. As the skydiver jumps out of the plane, they will fall accelerating towards the earth with a force due to gravity. Okay, gravity is actually an acceleration, which is approximately 10 meters per second squared. So he's going to fall towards the earth with an acceleration of 10 meters per second squared. The force due to this, which we will get to in Newton's second law, is the mass times the acceleration. So our acceleration in this situation is gravity, the mass of the skydiver. So the force due to gravity is going to be the mass multiplied by 10 meters per second squared. So our skydiver is falling to the earth with a speed with a force due to gravity. As they fall, there will be air resistance pushing up against them. We know that this will be an unbalanced force because they are rapidly falling with a changing speed towards the surface. So they will be accelerating towards the ground. Okay, once they jump out of the plane, they're going to accelerate towards the ground. So in order to slow this acceleration, the skydiver is going to release their parachute. This parachute increases the surface area, which means now you have air resistance working against a much greater surface area. So we increase the size of the air resistance. And what will happen initially is that the skydiver will be pulled upwards as that air resistance is initially greater than the force due to gravity. As they fall, the vents kick in and they'll accelerate up for a little bit, and then force due to gravity and air resistance will equal out, and they will start to fall towards the Earth with a constant speed. Okay, once that constant speed is reached, it is terminal velocity. So the terminal velocity is the constant rate of falling, or the constant rate, the speed of which an object falls at its maximum speed. So once it reaches that maximum speed, we call it the terminal velocity. And this remains constant for the rest of the fall because the air resistance and the force due to gravity are balanced out. Okay, so the skydiver themselves would reach a constant velocity, which would be the terminal velocity, but we can actually slow that down even further by providing the largest surface area for the friction to work on. So now our skydiver is falling with a constant velocity towards the ground, because our forces are balanced for air resistance and our force due to gravity. But what happens if a wind blows? All of a sudden, if we have a wind blowing, we're now going to have an unbalanced force that will push our skydiver off course. They would now move in the direction of that wind. Okay, so when we're looking at whether or not forces are balanced or unbalanced and what would happen to the chords of motion, okay, then you need to consider what happens if our situation changes. So while they may be falling with a constant velocity, we may change the direction of their fall by another force coming in, such as the force due to wind. So that's Newton's first law. We need to be able to state it. So basically the object will stay in motion with a constant speed unless an unbalanced force acts upon it. So that will be stationary or a constant speed. Okay, so in order to change the motion of an object, there must be an unbalanced force acting on it. If an object is stationary or moving at a constant speed, the overall forces acting on the object must be balanced. So the vectors must be equal in size but opposite in direction. And then we need to consider all the forces acting on an object at a specific time and draw a diagram of the vectors in order to be able to work out if our forces are balanced or not. And that's it for Newton's first law.